So welcome everyone to the Young African Scientists platform. We've started the recording, so if you approve of it, let's see your hands in the chat column so that we know you approve of us to record this meeting. All our meetings are recorded and posted on our website, that is yaslinkup.com/the-engine. And then we have a YouTube channel that is Young African Scientists YouTube channel. So you can also go there for all the lectures that we have done already. I'll be posting the link for attendance. Once the lecture starts, I'll put it in the chat box. And all you need to do is to click it. There is a form that will take your professional ID, your name, and then you just mark attended. And so that will come shortly during the lecture. I'll be posting it multiple times for those that will be joining late so that they can also join. Attendance forms 80% of your assessment, and that is because we will need you here to interact with our teachers, and we need you here so that we can verify that you are indeed participating in this course. We are starting a new system of attendance, and we'll start today, where if you miss today's lecture or if you miss any of our lecture, you can go back to the website, watch it, and then questions will be given in the lecture. You answer those questions, and then you send it to us, and then we will mark your attendance for you. I've received a couple of messages from the students that this time, sometimes they have lecture and group meetings and it's difficult for them to join. And so we are bringing that particular provision so that even if you miss it, you can go back, watch the video, do that easy test, and just mark your attendance. So thank you very much for being here. And I'm going to ask our teacher for the day, Trustin, to come in, introduce himself, and then start the class. If you have any issues with your code, your professional code, send me a private message. I've seen some of you have sent me a private message. I'll answer it and I'll get your code to you. We have all the code here. So if you don't have your code, or if you've not registered yet, I'll also post a link for registration in there. And then, but if you register, you have to go back to watch all the videos that we are making available. Thank you very much for making time to be here today. And I would pass you on to your teacher. Trustin, you can unmute and introduce yourself to the group.
Thank you so much, Dr. Tabiri. All right, I'm going to share my screen now as I introduce myself. So my name is Trusting Inekwe, and what I'll really be talking about today is data preprocessing. What I really want you to do as you walk around this, as I go around the slides in this on this topic, is to really just think. And don't just limit yourself. Just think outside the box. Think about your data. What are some things you need to do on your data before you even go into the modeling aspect of it? All right, so I'm going to cover some topics, but before I go into data preprocessing proper, I'll cover topics like what is data, some data collection methods, data forms, the forms in which data exist, and some sources, examples, and some comparisons. And then I go into data preprocessing, where I talk about splitting your data into training and testing, data profiling, data transformation techniques, such as how do you handle missing values in your data? How do you reduce, if you have a data that has so much information in it, how do you reduce it? What's a technique to doing that? That actually helps with your machine learning model not being overworked or not having to do a lot of work. And then I go over some coding and I have some practice questions at the end. So please feel free to stop me at any point. If it's possible to make this very interactive, I'd really like that as we continue. So the big question is, what is data? I think in the chat, if you're able to chime in, just type, can anyone tell me what data is? I'm on the chat. I can see when you send a message. Does anybody want to answer? Okay. All right. That's fine. Somebody said it's machine learning numbers. Thank you. Anybody, any other person? One more. Let's do one more. Information. Thank you. Yes. Data is essentially factual information like numbers, statistics, observations. Thank you. Unprocessed information that is collected, processed, and used for analysis, decisions, or computations. But before I go further, what's the difference between data and data set? I see this very often. People use this words interchangeably. Can anyone just tell me briefly what's the difference between data and data set without asking ChatGPT or Googling? Anyone? I just need one answer and then I'll proceed so I don't waste time. Data set is a collection of a type. Group data. Okay. Well, thank you. Exactly. So data is really raw, unprocessed information. And then data set is when like you said, well collection, or you sort of structure your data. That's what you call data set. Now, data can be qualitative. For example, you have your data could have qualitative information like words, text, or it could be quantitative, having numbers. And in those numbers, it could also be discrete, maybe one, five, and it could also be continuous. Excuse me, like decimal numbers or fractional numbers. Now, what are some data collection methods? We could see primary, it could be collected in the primary form where you're the person who is actually going to use this data, is, organizes a survey or questionnaire, collect directly or is directly involved in collecting this data. Or it could be collected in a secondary process. Maybe you use the data, government data, or you perform what they call web scraping. Um, and then you get data. Other collection methods, it could be from automated means like clickstream, social media, data logs, sensor information, and things like that. Now, data can be in various forms. It could be structured, for example, customer information, in a table and, having rows and columns, and semi-structured, for those who are very familiar with things like JSON files, where there's a structure, but it's not really binding that structure. So it's not very rigid structure. So that's semi-structured. And then it could be unstructured, maybe sensor information or sensor data, emails, social media, things like that. So those are some forms in which data could exist. Now, this is just giving an example of the different ways of the different forms in which data could exist. We could see data can be unstructured. Here we see like almost like a JSON file where it's semi-structured, and here it's structured. So data could be in any of these forms. And interesting enough, we have machine learning models like transformer networks that could actually use unstructured data. But typically, and what we will really focus on today is looking in the space of structured data. So I provide very high level explanations of data and some pre-processing approaches. So this is just a comparison between structured and unstructured data. Structured data can be displayed in rows and columns. Unstructured data doesn't, cannot be displayed in rows and columns. Structured data has numbers, dates, strings. Unstructured data can be audio data, image data, things like that. I think something that was really interesting for me here was the fact that 20% of enterprise data is structured, while 80% is unstructured. So that was really surprising to me. Structured data requires less storage because it's already processed or curated, and so it doesn't need a lot of storage, while unstructured data requires a lot of storage. And of course, because it requires less storage, you could easily manage it as compared to unstructured data. Now, imagine you have gotten your structured data. What was the next step? So we're moving away from curating the data set itself to just, okay, you have a structured data. What do you do next? The first step you do is to divide your data and keep the test portion of the data away. Now, I'll explain what that means. Now, before you apply your machine learning model, one of the first steps you do is to divide your data into a training set, which you use for your training, which you also apply your pre-processing on, and then you have your test data set, which you use to evaluate the performance of your machine learning model. I would just want to ask a quick question in the chat because I like being interactive. What's the essence to which you divide? Why what's the reason why you split your data between training and testing? Just one answer in the chat, if possible. Anyone? Okay. Verification of model. Thank you. Yes, so that's one reason. But really, what you're trying to do is to prevent overly optimistic result. Okay, thank you. Good answers. Um, excuse me. So the real reason why we split the data between, I say generalized, that's good as well. The reason why we split data between training and testing is really to ensure that um, we have a version of the data set that is just unprocessed. So before we pass this data into a machine learning model, we have to do some pre-processing because, like they say, garbage in, garbage out. That really applies to machine learning models as well. So if you give a machine learning model a really crazy data or not well-structured data, depending on the type of model you're using, and then you get bad results. And so we need a data set that we could do a lot of pre-processing and cleaning and things like that. And then we need a version that we could keep as, okay, this is just the direct data that no changes have been made to. So let's say you have a full data set. The first thing you do is you identify your input features and target features. So these first boxes here, you could say those are the column names. So or feature names. So you identify your features and your target. So what you do is you split your data into training and testing. So X-train is the input features for your training set, and Y-train is the target feature for your training set. The same applies to your testing set. Now, your training set is used for training, as the name implies, and your test set is used for testing. So X is input features, Y target features, X-train input for training data set, and X-test input for test data set. Now, how do you split your data into sets? So there are various approaches to do that. So I'm just going to highlight a couple of them here. So you could say, okay, I'm going to randomly just select rows in my data set um, and put randomly in a training or randomly in a test. So like you see over here. Or you could say, I'm going to characterize my data set into a certain form where I, let's say if it's a data set on patient information, patients that have a particular type of disease, um, I'm gonna um, I'm gonna put them in a category. And so stratified sampling is essentially categorizing, and then you select um, your training and test set from those categories. Or you could use a systematic approach to sampling, where you use maybe a mathematical number or a hashing approach or you could, use cluster sampling and things like that. So depending on what you want, you use the sampling approach that's preferable for you. In my some of my previous work, I've used health data set, and really we were, for the trainer test splitting, we were very interested in only taking unique patients to the training and unique patients to the test. We didn't want the information being leaked between those two sets. And so we used essentially individual sampling, which is not really shown here, but that's an approach. Now, imagine you have split your data sets and selected your training set. What's the next thing you need to do? So now we're only working with our training set. So we've kept our test sets elsewhere, and now we have just our training set. Now we'll perform data preprocessing on the training set. And data preprocessing is really the second step in the machine learning pipeline. So you have your inputs and you analyze your data, you do some preprocessing, you do some training, which is to find patterns here, and you make predictions. So we're in this second phase, which is where we analyze the data. So what is data preprocessing? Data preprocessing transforms raw, messy data into clean, structured format that's ready for a machine learning model. So data processing could be in various forms, things like data profiling, um, data cleaning, data reduction, data transformation, data enrichment, and data validation, things like that. So I'm going to touch on some of these in my presentation. So the first one, data profiling. What is data profiling? It's just a way to explore or visualize your data. And the goal is to better understand your data set. So let's say you get your data set. One of the very first things you need to do is to just look at this data and understand it. What are my features? What are my, what's a good model for this? What is the distribution of some of the features if it's a numeric data? You want to understand all those things before you take your next step. So I showed two images here. So this is a map of California in the US. Um, you can see we plotted two features, latitude and longitude here. And we have this image here. But then this tells us, this is not very informative because you wouldn't say as longitude is increasing, latitude is, things like that. But when you plot this secondary diagram where we actually is the same image, but with more information added to it. Um, we have latitude, longitude here, and then we have median house value, which is starting from 100,000 to 500,000. If you look at this image over here, you could see this blue indicates the water. So there's a big body of water. And then these red spots, red dots you see over here are close to this water body here, which is basically saying houses that are closer. So it's a these images were gotten from a housing data set. So what this is saying, houses that are very close to the water are usually more expensive because you have higher red values here, given their median house value. So these houses are more expensive if they are close to the water. And that makes a lot of sense because I think the goal of a lot of people is to have a nice beach house where you can see the water, you can go swimming and things like that. So houses around these areas are more expensive. So this is an example of visualizing or understanding your data set. Another thing we check for in our data sets, especially when we have numeric features or number kind of features, is correlation. Correlation essentially measures how two features change together. So this is an important thing we need to find out. Also, correlation helps in understanding the relationship within the data set. So some of the typical images you plot in your data analysis approach when you have numeric features is two-dimensional diagram. So we have a feature here, household units, and we have another feature here. And you can see that when you plot their values, you can see they are increasing. It's sort of increasing upwards. Now, what this is saying, as foreclosure is increasing, because towards the right is increasing, as foreclosure is increasing, as more houses are being closed, you have more housing units. On this other one, you can see the less educated people become, the less number of educated people we have, the more unemployment is increasing. Now, in terms of correlation, we could make some interpretations. For example, when it's going upwards like this, we say a strong positive relationship. When it's going downwards, we say strong negative relationship. For this one, we don't really see a relationship because connection between having pets and going to college. So when you plot the interaction between those two features, there's really no relationship here. Another way to visualize correlation is through what we call a heat map, where we see variable one with itself, of course, is very highly correlated. And so we have a one. One indicates very correlated. At zero, depending on which type, I think this is a Spearman correlation. So you have negative values. Negative values also, if you have a negative one, that means strong negative correlation. So we can see variable one and itself is very correlated. But when we look at variable two and variable one, there's really no correlation here. Now, how do we come about this and how do we come about this? This is just a visualization of correlation shapes and their values. So when it's going upwards like this, it's a one. When it's not really clear that it's going upwards, it's a 0.8, but it's still going upwards. Here, there's really nothing you could infer from this. And then when it's coming down and it's clear, you can have a negative one. When we have images like this, we don't really see a correlation between those features. So correlation is really just the linear relationship between two features. Now, I'm here. I'm showing you I'll show you an example of a scatter matrix plot. What we call a scatter matrix plot is a grid of scatter plots that show the relationship between multiple variables in a data set. So in that housing data set, which I mentioned previously, we have features like median house value, median house value. We have median income. We have median house value. So we can see the median income and median house value. You could see somehow it's increasing. It's essentially saying as income is increasing, there's a higher chance that you go for a better house. Although it's not very clear, like we see in this image. So if I run a Python code to really isolate median house value and how it correlates with other features, specifically, or before I go into the specifics, we can see median house value correlates with itself, which is very strong. One, when it comes to income, yes, it's there, but it's not very clear. So we have a 0.6, which is quite on the high side, but it's not one. And so when we plot that median house value and income, we can see it's going upwards. So you could say it's close to one. Now, in terms of correlation, there's what we call multicollinearity. That's when two features are correlated with each other, like we saw in our previous image, median house value and median income. Now, multicollinearity could be a bad thing, and it could also be a good thing. It could be a bad thing in the sense that when there's correlation between two input features in our data set, it can be bad for some type of models, especially very basic machine learning models like linear regression and things like that. But when you have correlation between input and output feature, this is good. I'd like to ask the people in the chat, or I'd like to ask you, what could be a reason for this? Anybody want to help? Just one answer. I just once I get one answer, I move on. Anybody? Like they say in the auction, going once, going twice. All right, I'll answer. So Okay. Correlation between input data can interfere. Um, Let me see. Between input data can interfere with the model's work. Yes, yes, exactly. Between input features influence the metrics. Thank you. So when you have correlation between two input features, when you're using models like linear regression models, um, then there are certain assumptions that a linear regression model assumes your data to be in. And so when it's not in that, it doesn't fulfill the assumption, then you can have problems. One assumption is what they call independent and identically um, um, different, something like that. I don't remember the exact terminology. What is basically saying an assumption is two input features must be independent of each other, um, and they should not have any correlation between each other. So when you plot the linear regression model, you want each um, input feature to be independent. So how it impacts the model generation should be independent. So when you have two features that go around the same way or correlate with each other, it can impact um, the model creation. So I'm just speaking in very high level terms. So you just have a mental picture of what it is. Now, when on the other hand, when you have correlations between input and output feature, this is good because that's what we really want. We want to have a data set where you could clearly see how the input features are affecting the target or output feature. And so that's a good thing. That's something we really want. And so that's why it's a good thing. Now, I have an example here in this example data set where we have input features and a target or output feature. Now, you can see length and height here. Um, let's assume they are correlated. So length and height input are correlated, and when you're using this could imply redundant information, and so it could really make the model um, 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 do more work, if I could put it that way, and so it could increase the training time. So this could be redundant information, um, and then it could negatively impact models, like I mentioned earlier, things like linear regression model. On the flip side, what you really want is you want a data set where each of these features are independent. They're not really correlated with each other, um, but they should be correlated with the output feature to some extent. And so when we have multiclinarity as a bad thing, what are some ways in which you could handle that? One approach is to leave it as it is, and then use a more complex model where correlation doesn't between the input features don't really affect its estimation. And that way is to combine features. For example, we could combine length and height. Let's say we say every length value multiplied by the height value. So we have a singular feature. And that approach is to remove the feature. Maybe I say, okay, I remove the length and I only leave height because both are giving me the same information. So that's another approach. And this could help with reducing the training time. So now we're going to data cleaning. What is data cleaning? Data cleaning is detects and fixes issues like inaccuracy, missing values, formatting errors, or duplicates. So that's really what data cleaning is, detecting and fixing those issues. Now, it also helps to improve data quality and reliability for analysis and modeling. So when we have things like missing values, that could be an inaccuracy. And so we could make inference from that. We could ignore it. We could delete it. We could make imputations. So those are a form of data cleaning. When we have what we call outliers, outliers are values that are not possible to be calculated. For example, if I have something like height, let's say the tallest person in the world is 8 feet. So if I have a data set where the height is like 20 feet, I know that's definitely an outlier. That person is probably touching the skies at this point. So that's an outlier and that's not possible. So what do? We could delete those outliers. We could flag those outliers. Another inaccuracy could be duplication, where we have values duplicated that which is not supposed to. Maybe we'll have features that are duplicated. That's it, an example of data cleaning. When we have irrelevant data, deleting that, that's an example of data cleaning. So now I want to go into missing values. Now, there are two types of, like I mentioned earlier, there's numeric data and there's qualitative data. So data that has text and things like that. When we have a feature that is numeric, and then we have missing values in that, there are some approaches to handling those missing values. One approach is what we call forward fill. So we see over here, for example, on row 2, wind speed and row 2, we have a none here, and we have a 7.0, and we have a 9.0. But when we go here, number 2, instead of that none, I have a 9. So forward fill is replacing this none or this empty value with the previous value, like you see here. Vice versa, we have the backward fill, where we're replacing the empty values or missing values with the next values. Another approach is just deleting the feature. So you see in this data set where we have city, salary, married, and then we see so much of the features are missing. So an approach could be to delete. But I'll be very careful with this approach because let's say in an African country, you have a data set from an African country, let's say like where I'm from, Nigeria, and then you have malaria happening, and then you have a data set where fever is one of the most important feature. But then in the data collection approach, fever was not really entered into the data. And so you have a lot of missing values. Do you delete fever? I don't think it might be a good approach because then you miss a very critical information in your data set. So, but on certain context, yes. Before I started this presentation, I said something about think outside the box, like think what, because a lot of data preprocessing you do have a lot to do with your own self-judgment. And so based off of that, you make judgments on your data set. So in this case, we remove the salary feature here. Now, another way to handle missing numeric features, like we see here, is use some of their statistical information, like mean, for example. Here, all these non-values are replaced with their mean values. Other approaches could be median, could be mode, and things like that. Now, when we come to categorical values, when we have a feature that is categorical, how do we deal with missing features? Now, one common way is to replace those missing features with features that are the most frequent. So that's one approach. Some other approaches is to actually, and I think this also applies to numeric feature as well, is to have an indicator variable, which is you create an extra variable that is indicative of when a value is missing. So where value is missing, you have a 1. Where it's not missing, you have a 0. Maybe that could be a useful information. Maybe those things that are missing are actually important for them to be missing in the data. So when you think about that, then you decide if you should create an indicator variable. Now, there's some other advanced imputation techniques. One is using machine learning models to predict missing values. For example, you use models like k-nearest neighbors, KNN, and then we could also use regression-based imputation. So when we talk about KNN, I'm just going to very high level show you a visualization to have a mental understanding of what KNN is. So what we do in KNN is we create clusters. So you have a cluster, or should I say categories. You have a category of people in one side, you have another category of people. Now we have a missing value in our data set. What category does it belong to, or what cluster does it belong to? Now, KNN definitely uses sort of distance estimation. So you can see this red, which is the missing value. Um, it's it's closer to the green as compared to the yellow. And so what KNN will do is to make an imputation of a value that is more closer to this cluster. And so that's what we call nearest neighbor. So NN, which is nearest neighbor. Do we have a, okay. I was just checking the chat. Oh, so this is essentially KNN itself, KNN imputation approach. Now, machine learning models, they require numbers. So machine learning models don't work with text, except maybe you're working with large language models, but even that, there's still some form of encoding. So what we call encoding is essentially converting a text or something into something. So let's say I have low, medium, high as values in a certain categorical feature. How can I encode those things into numbers? So I could say low means 0, medium means 1, high means 2. So every time I see an occurrence of low, medium, high in any shape or form in that same feature, I replace those texts with numbers. So that's what encoding. So that's the only way a machine learning model can work. So when we have categorical values in our data set, we need to encode those values so the machine learning model could work with it. So there are some common techniques. One common technique is what we call one-hot encoding. We also have ordinal encodings and some other ones as well. So I'm just going to show you what one-hot encoding is. So let's say I have a data set with a feature. This feature is called origin. It's a column. It's a feature. In origin, I have USA, Japan, Europe, USA, Europe. Now, one-hot encoding, when you apply one-hot encoding to this feature, is you create new sets of features. So here, the nomenclature here is origin underscore USA, origin underscore Japan, origin underscore Europe. Now, anytime there's an occurrence of USA or of that value, I put a 1. So here I have USA 1 and USA 1. For Japan, I have 1 and the rest is 0 because only one Japan came. And then here I have Europe 1, 1. So one-hot encoding creates new columns that have binary values, 0 and 1, where 1 is where that value actually occurred. So this origin column is now removed from the data set, and then you have this new set of columns with numbers. Now, there was a typo here. This is not encoding, my bad. This is feature scaling. I meant to put feature scaling here. So feature scaling is a way to essentially I could say encode as well, numeric features. So let's say, for example, you have a data set where it has the age of people as a column. So people's ages go from, let's say, 1 to 100. Nobody really lives up to 200. That could happen. But let's say we have 1 to 100 age column, and then we have another column where we have the salaries of these people. And so salaries could have things like 10,000, 100,000, and things like that. When you create a machine learning model and you don't scale those features, and you leave those features as is, the values of the larger values actually dominate that model. And so you create a biased model. And so to avoid that, we do what we call feature scaling or normalization, standardization, things like that. And so we convert those values into a fixed range of values. And every numeric feature in that data set, we also convert it to that range. So normalization is just how those values are calculated. Is you take the value. So here we have an input of 0. 0 is this input value minus the minimum value in that column, which is 0. 0 minus 0. And then the maximum value here is 5. 5 minus 0 here. So 0 over 5 it gives you a value of 0. So rather than having each of these specific values, what I have is a number between 0 and 1. On the contrary, standardization has values between -1 and 1. Excuse me. I have another example here um, that could make some better clarification. As I mentioned earlier, we have age and we have salary. So salary is in the unit tens, 100,000, tens of thousands, while age is in tens. So we have to normalize this to give it a range. So normalized age is this, normalized salary is this. Um, and so this essentially helps the model not to do so much work. Each number in a computer can be, is represented in bits. And so you could have so when you have really large numbers, you need a lot of bits for that. So when you put these things in normalized forms or standardized forms, then essentially you don't have to use a lot of bits. And so by that, you reduce the training time. It's more easier for the model to work and things like that. I'm almost done, and then we'll go to something more practical. But what I wanted to show you here is what we call skewness and kurtosis. So skewness indicates if the data is tilted more to one side. What you really want in when you have a numeric feature in your data set, what you really want is it to have what we call a normal distribution, especially when you're using models or especially when you're using basic machine learning models like linear regression and things like that. And in reality, in a real world setting, you don't really see features that follow this ideal normal distribution. Rather, you see features that are what we call left skewed. So you have higher values towards the right, and sorry, you have more occurrence, more like more occurrence of values in a certain position in left skewed towards the right, and then it's skewed towards the left. Or on the other side, we have what we call right skewed. So skewness could be a problem. And so those are some things you need to pre-process before you actually apply it to a machine learning model. On the other hand, we have what we call kurtosis, which is essentially the peakedness or tail behavior of a numeric feature distribution. So what you really want is a feature that's in the middle and not very high. When you have things like this, we have the potential for outliers or extremely high values. So you need to do some sort of transformation to convert your numeric feature from being skewed to being more resemblance of a normal distribution or to be mesocritic, which is the middle one here. So an example way to address this is what we call feature transformation. So things like log transformation or power transformation. These transformation approaches, they stabilize the variance and reduce the impact of extreme values or outliers. It could also help to provide clearer patterns in your data set and provide better prediction. So for example, in a data set that is right skewed like this, so you have more values towards the left here and it's reducing. You have less occurrences here. When we perform log transformation, it converts this to something of this form. When you're using a model like linear regression, some of the assumptions or expectations, let me put it that way, that your linear regression model wants is something that is close enough to a normal distribution, so it can perform a much more effective training. And so log transformation is one approach you could apply to right skewed distributions. Another approach is what we call power transformation. So here we have a left skewed numeric feature that is going this way. And so when we apply power transformation, it converts it from this to this. Now, you could have a situation where in your data set, you could have a situation where your data set is high dimensional. What do I mean by high dimensional? I have a significantly large number of features. You could have data sets where those number of features could go as maybe as large as 700, 1,000. And that could be a lot for your computer or for, if you're not using a very high powered machine or computer, that could be a challenge. So an approach in data analysis is to reduce that dimension to a smaller set while maintaining key information. One very common approach to doing that is what we call principal component analysis. So it's a dimension reduction approach where it converts your lots of features that you have into what we call principal components. Now, these principal components are new features that are being created that you pass to a machine learning model. But these principal components, for example, principal component 1 will contain the information of multiple variables. So it's just almost like so many variables, their information is sort of passed to this principal component. And then you don't have to have so many features this time around. You just represent all these features with a singular feature. Now, usually principal component 1 is the one that has the most usefulness. And then principal component 2, and then it goes on like that. So principal component 1 will have features from, let's say, 1 to k, where k is less than n, or k is not the whole set. But in the principal component generation, you have principal components as much as the number of features. But each of the principal components is only representative of a set of features. Now, how does this come about? I'm not going to go into the very much detail of principal components, principal component analysis, because then we have to go into things like matrices, covariance matrices, and things like that. But essentially, when you look at this image, you have a feature Y, have a feature X, have a feature Z. Now, each of these features, when you plot them in a three-dimensional space, this is how they look. And then this is the values from this three-dimensional space. Now, what principal component does is it says rather than using this original space or dimension, I'll create my own dimension in the direction of the maximum variance. So how do I explain this without going very deep? But essentially, you want a dimension that really explains or that really you could map your data set to. So here you see we have a principal component 1 here that is plotted or that is in between these features, in between these values. And so this now represents, I could say in this context, these three features. So principal component 1 explains most. Then we have principal component 2, which cannot really explain a lot because it's orthogonal to this principal component 1. And so if you look at this image here, you see maximum variance can be explained by principal component 1, and just a few can be explained by principal component 2. So we move away from this XYZ to this two-dimensional space. So we've reduced the dimension from three-dimensional, to two-dimensional. And so we have principal component 1 and principal component 2. Now, I've done a lot of talking. I just wanted to give some room to questions. If anybody had some questions before I go into the coding.
If you have any question, you can unmute at the moment. The restriction on muting has been removed. So You can just unmute and ask your question if you have any question on any part of the lecture.
Yes, sir. How you doing, Dad?
Go ahead.
Yeah, yeah. As I see from the 3D space, I know the values of each of the things will be having three coordinates. How do we reduce the coordinate into two if we have numerical value? How do we represent the numerical value into the two-dimensional value?
Okay. Thank you. Thank you. Great question. I could go into like the mathematical, but I'm not sure I want to go that deep. But essentially, there are things like covariance matrix you estimate to see how the features interact with each other. And then there's what we call eigenvalues and eigenvectors and things like that. So those are some deeper, and I'm happy to chat about them maybe after the meeting. Those are some ways. So essentially, your principal components are those eigenvalues. And so eigenvalues essentially are a way, in a very simplified form, could be in a way, constructs or things that um, are able to explain most of the features. In matrices terms, eigenvalues are a way to represent the direction or magnitude or direction. I don't know. I don't want to go very much into the detail, but in terms of principal component itself, you have a three-dimensional space like this, and then you have your features. I mean, you have these values where the values from each of these features intersect, right? And then you the principal in Python, we have libraries that do all this principal component estimation for us. But really, you have principal components being derived like that. And then this principal component line is basically minimizing the error between these features. So when you create a machine learning model, let's say, for example, this one, and let's say this is not a principal component one. Let's say this is just a line that explains the data. You say your linear regression model plotted this line. Now, the difference between this value and this line is the error. So this line is what we call the predictive line. This value itself is what we call the actual value. So when I have a value here and I go upwards like this, and I go to this predictive line, and then it makes a prediction here. So the value here is what it's predicting. But in the real sense, when it goes up like this, in the real sense, in reality, if we're not using the predictive line, it goes up to this point and goes up to here. This is the actual value, but then it's predicting here. So that difference is what we call the error. So when you plot your principal component line here, you're essentially plotting a line that minimizes the error between these features. So if I had a line, I don't know if I could write on this. Let me see. Annotate. Yes, perfect. If I had a line that goes like this is not a straight line. I apologize. We can see we still have a lot of errors. We still have huge errors, errors here. So essentially, principal components, there's some differentiation and things like that happening where you eventually have a line that could explain the variance. I mean, that goes in the direction of the maximum variance here and things like that. And so this becomes your principal component one because, for many reasons, it goes in the direction of maximum variance. It minimizes the error and things like that. It can really explain the data much more. As compared to principal component two, when you look at it, you can see there's a lot of error between the actual values and what it can predict, and things like that. So I don't know. I said so many things. Maybe I don't know if I help in any way. Sylvester?
Yes, sir.
I don't know if I helped in any way.
Yeah. At least I got little understanding on what you said. Thank you.
Thank you. Any other question?
Yeah, Dr. Trusting.
Yes.
Good evening from my side.
Good evening. Good afternoon from my side.
Oh, okay. That's great. Yeah, thank you very much for the explanation.
Yes.
I just want to ask relative to what Sylvester Gono said.
Yes.
Now looking at a 3D, let's say a 3D analysis.
Yes.
Now I saw in the right hand graph where you resolve into two components. Is it always the case like XY, or do you have to resolve maybe ZX or YZ? Is it always XY component?
No. So are you asking in terms of the names? Is it always, or could you clarify your question?
I think
Yes, in terms of the
the
name.
dimensions.
Oh, the dimension.
Yeah.
So,
Yeah.
so are you asking,
The
is it always,
direction, sorry.
oh, are you asking, is it always two-dimensional? Is it always, two-dimensional, things like that? Is that your question?
Yeah, the two-dimensional, like, do you always consider, for example, the X and Y component? Why not X and Z?
Okay, so this is these values you see over here, these values are representation of the three-dimensional, so X, Y, and Z here.
Okay.
So, oops. Okay. So X, Y, and Z. So it's a three-dimensional. I mean, it's representative of all the dimensions. So each of these dimensions are features, right? So when you look at all the values for different features, and then you plot it, the scatter plot. This is what it is. So it could be it looks at all the features, so it's multi-dimension. We can't really show it here. So it looks at everything, and then makes inferences and then converts it to principal components. I don't know if I helped.
Hello, Trusting.
Yes.
Okay. I just want to say something.
Okay.
I'm not going to be talking from the perspective of a machine learning expert.
Yes.
I'm just going to be talking based on intuition and maybe a common sense experience. So if I'm wrong, please correct me.
No problem.
So from the dimension perspective,
Yes.
I believe instead of giving the machine model a three-dimensional data set, and when you know there is no data set in the Z direction, the machine learning is going to interpret the three-dimensional space. But based on you as a human thinking expert,
Please,
knowing that there is no...
its network is very bad. If you can just adjust himself so that we can hear the question.
Okay. Can you hear me better? So what I'm trying to explain is, instead of having the machine model explain a three-dimensional space, when there is no data set or there is no variable, like variable 1, 2 to variable n in the z-axis, it's best to reduce it to two-dimensional spaces, S and Y, because we have data sets in the SY plane. But if, for example, these data sets were in between S and Z, and there's none in the Y direction, the 2D space will be reduced to the planar space of S and Z. So the whole point is trying to reduce the model to where you have or reduce your data structure to where you have variables that are of principle that has information for the model to process. That's for the conversion from 3D to 2D space. But for using the principal PCA, like you mentioned, which is a principal component analysis. So what I understand from this, which may be of, which may help others to also understand is this. Instead of, if you look at the variables that you have here, without the red line and the blue line, you have maybe up to 13 dots, which are the variables, so to say. But when you reduce those dots based on those lines, it's just like using line of best fit to represent the direction of variable in your data set. You kind of reduce the data set to those lines. So instead of interpreting 13 dots or 13 variables, you are more or less interpreting 2 lines, which is the red line having the a larger representation in the X and Y direction, and the blue line having to represent the data in the direction of the blue line, so to say. So the point I understood is, instead of interpreting or giving your machine model to analyze maybe 13 variable data points, you are giving your machine model 2 lines to analyze, making the whole analysis simpler for the model. I don't know if that kind of make the explanation easier to understand. This is how I understood this dimension reduction. Yeah.
Thank you. That's awesome.
Yeah, Dr. Trusty.
Yes.
Yeah, yes. I envisage this to be like in mechanics. When you see an object moving in space, if you see that you cannot analyze it in 3 dimensions, you can draw the axis in a direction, then orthogonal to that axis, you draw it so that it can be in 2 dimensions, then the analysis will be easier. This is how I see it.
Yes. Yes. That's how it is.
I think, Fad, you want to say something?
Yeah.
Okay, go ahead.
Thank you. Thank you so much for your contributions. I think maybe I was not clear on certain things. When we look at this X, Y, and Z, they're basically representative of each of these variables. So this set that has, oh, okay, Fuad, you want to say something? Go ahead.
I do have a simple question actually regarding this PCA analysis. Actually, as one of my friends says, I'm not basically focusing from machine learning perspective, but what are the factors that determines how much PCA units we use? In case sometimes you might use PCA analysis up to 5 or 10. What are the factors that determine in case of this machine learning?
Okay, so if I get a question, what are the factors that determines how many?
Is my question clear?
Yeah, so your question is, what are the factors that influence the amount of principal components you select eventually? Right? Okay, Fuad, I can't hear Fuad anymore.
Yeah.
Okay.
Yes.
All right. So again, there's a lot of self-judgment people make, but ideally, everyone selects principal component 1, because principal component 1 can explain a lot of the variables in your data set. So you definitely select principal component 1. So sometimes principal component 1 could explain about 90% of your data set. So, and then maybe principal component 2 explain like 5%, principal component 3 maybe like 3%, and things like that. So it's up to you, right? You usually have principal components as much as the number of variables you have, but then you select the ones that maybe up to 100 that really explain most of the data set you have. So it's like I said, you think about it. and then you make self-judgments and things like that. So it's self-judgment, I'd say. But if you could find principal components that explain most of your variables, then you should be good to go. I hope I answered your question.
Yes.
Okay. So I'll say one last thing, and then we'll go on a short break. And
Yeah,
then,
Pastor.
yeah, Joey?
Joseph here. So I wanted to understand principal component analysis in this context. It's like there could be many features, but you are trying to select the most important ones for you to have the most critical impact on the target variable at the end of the day. Is that the case for this whole idea of principal component analysis?
So that's an understanding. So that's those features you select eventually could be all embedded in one principal component, and that's what I'm trying to explain here.
Okay, so let me just create a scenario so maybe I get it better. Let's say you have the personal information of an individual across races, right? So a white, Hispanic, Black, whatever, and then you have their name as part of the data set. You have their name, their age, their hereditary or family history, whether any of their parents or family members have been diagnosed of diabetes and things like that. And then you have their sugar level and all of those things. You're just trying to look at which of these data, like I just mentioned, could come together and then really give it an individual stands a higher risk of being diagnosed of diabetes or not. So that at least according to studies, we know Black people are more susceptible to diabetes. If you have parents or grandparents who've had that, they're more more susceptible to diabetes and things like that. So you try to put all of this information in blocks so that PCA1 is what has the most influence on the targets that's being susceptible to diabetes or not, then PCA2, then PCA3. So the further it goes, the less important it is to the determination of the target variable. Is that the case?
So essentially, and I'll need to run for, in less than 30 seconds. But essentially, that data set you mentioned with different races, but then you have features in that data set.
Yeah.
You have so many features in that data set, right?
Yeah.
What PCA is trying to do essentially is find a way to combine all those data, all those features into a principal component. So rather than having so many features, that singular principal component can explain a good number of the features. And so instead of having
I get it.
Put that principal component, like this, the transformation from this data set to this. So in this data set, variable 1 to variable k can be explained by principal component 1. So that's why instead of having these variable names, I have principal components in my data set now. So I transform my data set to this. And so now when I create my machine learning model, I have fewer features in my data set. And so I'm able to easily perform this machine learning and things like that. I'll need to run very quickly. I have to pick my son and then I'll be back.
All right.
All right. So I think what we have now is we should be able to identify different data sets and then do data cleaning and all those things. The reason why this is important for machine learning is it determines success. So if you have something like we've been saying, garbage in, garbage out. This is the main approach to be able to get quality data into the machine learning algorithm. The machine learning itself is not difficult. It's just based on the Python you've been learning. You just call the module, you just give it the data, and then it will just do the computation for you, and you can visualize your output. And so you can look at the graphs, and it can give you different relations and give you different ways to look at what is happening. But if you don't get your data part right, and you're not able to clean your data well and do all these things well, then it becomes difficult to actually get anything good from your data. And so yeah, we have a few people that have been working with data, and what I want to do is to Joey, if you are here, what are some of the things you've been doing with the data that you've gotten? And I think he had a data set for making solar cells. That's about 48,000 data sets. And he had to go in, remove some of them, add some of them, and then do a lot of things. So give a brief description of how you managed your data processing aspect of your project. Joey, are you here?
Yes, yeah, Dr. Sabri, I'm here.
Yeah, go ahead.
All right, so like you mentioned, we are trying to predict some processing parameters that could help us fabricate perovskite solar cells with optimum output, is the photo conversion efficiency. So like you mentioned, there's been some data that has been gathered since 2009. We collected that data from 2009 till 2024. As a matter of fact, there is a repository that have all these data sets. So it could be one of the sources for data collection. Aside the fact that you can collect them personally, you could also get them from some of these repositories. So you got them from the repositories, and then we first had to do a quick scan of the data sets. Now, the most important target of our project was the fact that we wanted to have some processing parameters and materials that comes together to give us a very good efficiency. So it means that if there are combinations of configurations that have no reported PCE, then we can't really make use of them. And so what we did was that to go through the entire data set, and all those that had no reported PCE, which is our main target or our primary target, we had to eliminate them from the data set. And then some of the data set has also had a lot of missing variables across the columns, and also across the rows and down the columns. And so what we did was that depending on the number of active data sets that were present in either a column or a row, we decided to eliminate. And so we started with 70%, that if more than 70% of the row, a particular row, the data entries or the cells are empty, then that entire row have to go. And then to the column as well, if more than 70%, then it had to go. So because the columns and the rows are intersectory, normally by eliminating a row, you reduce the number of features in the column. And so at the end of the day, we're also able to eliminate some of these unwanted rows and unwanted columns that had very little to offer in this very case. Then we'd also went ahead to do the PCA to Truston was speaking about earlier on. But before the PCA, what we also did was to do imputation. So after eliminating some of these columns and then rows, it didn't mean that now we had the entire data set 100% full. Still, there were some rows and columns that were empty. So for numerical features, what we did was that we used the MICE approach, the multivariate imputation by chain equations, to impute all the numerical columns.
Is back, so you summarize the thing and then he can take over. Yeah, go
ahead. All right. Okay, so we used the MICE approach, that's the multivariate imputation by chain equation, to do the imputation for all the numerical features. And then for the categorical features, what we did was that because we had a particular row in our data set that described the configurations of the cell, what we did was that if there's a particular row that had some missing categorical data sets, we compared that to similar configurations that had that thing we are looking for present in that, and then we use that as the imputation. So the term I coined for it, I don't know if there's a particular term for it, but the term I coined for it is imputation by similarity for the categorical features. So if two configurations are very similar, like they say the perovskite is a PIN, all of them are FAI based, the HCl is the ETL is titanium dioxide, HCl is pyrimethamine, then they have a similar configuration. In that case, for the categorical feature, we can look based on the fact that they have similarities. We can use the present feature in what is present to impute in the missing feature for what we are looking for. So that was some of the approaches. There are a couple of approaches, but maybe subsequently we can share that later on. So Dr. Tibri, these were some of the few approaches we used in the data cleaning. I think there were about 8 or 9 steps. These are the few I can share for now.
All right. Thank you so much. Just to, wrap up and then we'll go to the coding. PCA, as I mentioned earlier, we're trying to reduce the number of features. It's too many features, and how can we reduce it? We'll have to find some sort of linear combination of these features. And so when we have some linear combination of these features, we have PCA and things like that. There's a whole mathematics behind that. And so XYZ here are the features themselves that you're trying to reduce from so many features. So they could be multi-dimensional. Here it's just 3-dimensional I'm showing here. How can you reduce this multi-dimension that we can actually visualize, that only the computer can actually visualize or understand rather? How can we use that? How can we reduce that dimension to something smaller? So when we have a smaller set of features, then it's a lot more easier for the machine learning model to actually train and things like that. So that's really the idea behind that. All right, let's do some coding. But before I go into the coding portion, I wanted to mention that before you do your modeling, you have to select your model and evaluation metric. So we have different types of models. We have types of learning. We have supervised, unsupervised, and reinforcement. So the data sets I've really been showing you all along from the beginning are supervised, where we have data sets with labels. So you need things like supervised learning, where you're essentially trying to map your input to your outputs, and then you measure the error when you eventually create this, during the training process to see, did I really get this target feature? How close am I to this target feature? And then we have supervised learning, where we don't have labels. Really what the model is trying to understand here is patterns or make inferences from that data. And then we have reinforcement learning, where you have states and actions and things like that. Now, after you select your model, specifically for regression and classification, you have to evaluate. You don't just create a model, you have to evaluate to see how well is my model performing. And so when we use models like regression models, and we use metrics like MSE, mean squared error, root mean squared error, mean absolute error, R squared value. R squared is basically a number that tells you how much your inputs can actually explain your outputs. On the flip side, classification, we use metrics like accuracy, precision, recall, where TP is true positive, TN is true negative, and things like that. Now, for the practical example today, I'm using an example from the hands-on machine learning scikit-learn book. It's by Aurélien Guérin. The data set I'm using is called housing.csv, and it's from GitHub. Now, this housing.csv file data set has the following features: the longitude. So it's a it's the image I showed you previously on the map of California. So it's the longitude, longitude and latitude of houses. There's a total number of rooms, total number of bedrooms, the median income of the people who own those houses, and the median housing value, and how close they are to the ocean. I'm using libraries like NumPy, which is I don't know if I think the name is Numeric Python. So it's just a way to fast numeric calculations. Then Pandas is more manipulating the data sets themselves. Matplotlib is just to visualize. So, and then scikit-learn is where you actually select your models and things like that. So I have a quick image of what scikit-learn are, some of the methods in scikit-learn. So you have things like model evaluation, mean squared error, data preprocessing methods, model selection method, train test splitting, and things like that. So you could always just call these methods and then you have results. Okay. So I wanted to show you the textbook. So this is a textbook. I think everyone should get this textbook because it has a portion where you could see code examples. And the code I'm actually going to walk through for the data preprocessing is from this book. And so it's very, very helpful. And the way it's explained, it's not like a typical textbook. It's more like a cool interaction. I wouldn't say interaction, a cool explanation of, just machine learning pipeline and things like that. So I'd advise you to get this book. It's called Hands-on Machine Learning with Scikit-learn. It's more of a pragmatic approach to machine learning. All right. So I just got a question. How can we get a copy? Well, you should typically buy these books, but all right. I guess I can't say more than that. I cannot say more than that. But I think there are PDF versions online as well. So you could check for those and you'd find them. It might not be the best approach, but you have to do what you have to do. All right. So this is this is from the textbook, Chapter 2, End-to-End Machine Learning Project. I'm going to go over the code, but if you quickly look on the left here, you could see some of the pipelines I mentioned where you get the data, you do some visualizations on the data, and you do some data preprocessing, things like data cleaning. How do you handle categorical features, feature scaling? And then we'll talk about custom transformers, which is like a data transformation approach, but customized ones that Python actually provides us, or scikit-learn. Then we have transformation pipelines, which is you want to do some data preprocessing steps, but you don't want to do it for each feature individually or things like that. So you create a pipeline where you could actually do all those things at once. Then we talk about select and train a model, then evaluate. I'm not going to go into fine-tuning because that's beyond the scope of this talk. So I'll just end at the very basic prediction of a singular model. So when we go to the get the data. So if you go through that book, it provides a link where you could actually go to this what we call Google Colab. Google Colab is provided by Google, and I really like it because it provides a very quick approach to begin coding in data analysis. And so how you get it is basically you have a Google account, and then you just type Google Colab, then you press enter, and then you click here. You could create a new notebook. Let me click that, new notebook. And there you go. You can begin coding. It also provides some AI functionalities. So I believe everybody uses AI at this point. I think if you isolate yourself from AI, in a couple of years, you'll probably be forgotten. So it provides AI tools where you could actual type of text. How can I import libraries, and then if it's working fine, it's going to generate the code for you, and things like that. But so it has given me some codes. I could say accept and run, and then this is how you import libraries. And so it imports those libraries for you. As compared to using a different system, things like Visual Studio Code, things like Jupyter Notebook itself, those ones, they actually require to install libraries and then import them and things like that. But Google Colab has a lot of those Python libraries already installed behind the scene. And so all you really have to do is import. Of course, there are some libraries that you really have to pip install them. So let me leave this place. All right, let's have a walk through this code. So print statement is just to print this text. So if I run it, welcome to machine learning. This is just this portion here is trying to see the version of Python. Is it between 3 and 7 and things like that? So if I run it, so these are not important to us for today. So I'll just run them. Now, get the data. So we're trying to download the data from GitHub. It has a zip attached to it. So, and this is the link. So essentially, what's happening here, we create a function. In Python, you use def to create a function. And that function is called load housing data. You create a path for that function and things like that, and then you put the link. My goal here is not to go every line by line, but just so you can have an idea. When you get this book and then you click the link, you'll be able to, you can be able to walk through these codes line by line to really understand every line of the code. I think that'll be very helpful in your machine learning journey. So I run that. So I just created, I just downloaded the CSV dataset. Here it's called housing. So now, after I've gotten dataset, like I mentioned before, you want to just explore to have an initial understanding. So housing.head here is just printing the first 5 rows in the dataset. So when I saved the data here as housing, and I do housing.head. If I do this, housing dot, does it give me options? You can see so many options here that you could select here. So where's head? AFGH. So you can see head is here. So it's one of the possibilities you could do, and things like that. So housing.head, if I run it, gives me this. I see my longitude, latitude, median age, total rooms, total bedrooms, population for each district, for different districts rather, and households, income. I see house value, and I see how close they are to the ocean. Now, if you look carefully, you see that the ocean proximity is actually text data. And so, as I mentioned earlier, machine models cannot work with this. And so you need to convert this text to numbers at some point. Sorry, give me a second. Sorry about that. So housing.head gives you that. Now, housing.info is just to get some information on this data set itself. So what information can I get? When I do housing.info, I see all the columns in this data set plotted here. Provided here. So I have 10 columns, starting from 0 to 9. And then I see the data type. So when you see float, it's almost like it means numbers. Sometimes it could be integer, meaning numbers as well. But most of them have 0.0 or point something, so they are usually float. Then this object is for this ocean proximity, which is essentially this value over here. And so this is not a floating type value. So this is an object value. So also another observation we see here, when we look at the number of actual, so this is non-null here, basically saying not null values, right? For longitude, I can see 20,640 for most of them. But when I come to total bedrooms, I see 20,433. So that tells me that I have some null values in total bedrooms. So let's keep that somewhere in our knowledge and understand that, okay, total bedrooms has some null values. We're going to do some pre-processing on that as we progress. So when over here, I'm just counting the number of unique values in ocean proximity. So housing, ocean proximity. What's my ocean proximity? This is it. So I have near bay, near bay, near bay. I have other values as well. But they are, how many near bays do we have? We have over 2,000 and things like that. So this is just plotting it's counting the number of unique values in that column. Now, we want to describe the whole data set. How do we describe it? Using statistical distributions. So when we do housing.describe, we have longitude, latitude, things like that. But then we have their minimum values. We have their standard deviations. We have their mean values. We have their quartiles. We have their maximum values as well. So things like that is how, so housing.describe gives us that. So from here, you could tell your minimum value, you could tell your maximum value, you could tell the count. So we can see total bedrooms here again has only, has some missing values. Over here, I'm going to be fast about this. Over here, we have images path. We're creating a path here, and then we're making a directory. A directory is a path, essentially. It's almost like you're creating a folder. So we're creating an images folder. We're creating another end-to-end project folder. And in this folder, what we're trying to do is save images into that folder. So on Google Colab, if I go over here and I run this code, I have images here, images folder. If I click this, I have end-to-end project shown here. So when you're running this for the first time, these will not show. But when you run this, and then you run this this next code, here, what we're trying to do is plot a histogram of the numeric values in this data set. So housing.histogram. So we're only plotting the numeric values, their distribution. So things like longitude, latitude, anything number here, that's what we're plotting, histogram. So if you see, we have save figure. So we're calling a method here, calling a function. We're calling this save figure function. So when we run this code, we're showing these images. So when you go to end-to-end project here, what's the name of the image? Attribute histogram plots. You can see attribute histogram plots here. And then you could download those images and things like that. All right, those are not very important, so I'm going to skip a couple of things here. So as I mentioned earlier, one of the first things you do is to create a test set. As I showed you, so this is essentially to ensure that you have something unique, or you have something that is a representation of reality before you start doing your data preprocessing on the training set. So here we're just creating a test set. As I mentioned earlier, there are various methods to create test sets. Here, what we're doing is we're creating a method here. It's called shuffle and split data. So we shuffle the whole data set using a random permutations, and then we split the data set. So if you see shuffle and split over here, it's the same shuffle and split over here. So this time around, we're passing housing and 0.2. 0.2 is representative of this test ratio. So shuffle split Shuffle and split takes in data and test ratio. Shuffle and split here, we're passing in data, which is housing, and split ratio. So when housing and 0.2 goes here, data, so it basically calls this function. So we go here, and then we shuffle the whole data set, right? So housing is here, housing is here. We shuffle the whole housing using the length of the number, which is about 20,000 something, total number of samples. And then we multiply that by the test ratio, which is our 0.2. So we'll get our test set. So for example, 0.2 times 100, that's 20. So 20 samples. If we had 100 samples, 20 samples will be given to our test set. And over here, so in Python, I'm only going to explain some of the very basic things so you can easily follow. So when we have something like this, with a column here, if I had a 0 or if I had a 1, it's basically saying select the rows starting from 1 to this test size minus 1. So what's happening here, I have my test size, which is, let's say 20, for example, and I put that 20 over here. So I'm selecting the first set of rows, first 20 set of rows. So that's 0 to 19. And then my training will start from the 20th, which is the 21st item, to the ending. So I'm sorry, that might be a little bit confusing, but I don't want to go very deep details, so, because of time. Now, what we're returning here is the index location. So after we've gotten our test indices and train indices, we're returning the number of rows, or we're returning rows that fall into those indices, right? So here, where we call this shuffle and split and pass the housing as 0.2, this first thing we return here before the comma is the train set. And the next thing we return here too as well is the test set. So if you see from our 20,000 something, the length of our training set was about 16,000. Usually training set is usually more. And then the test set is 4,128. So this is 20% of the 20,000 something we had. Now, in machine learning, something of interest is we want to be able to run the same model multiple times and get the same results. So one way we do that is what we call random seed. And it's typical, a lot of times people use the number 42. So we're using NumPy library, which I mentioned before. So we import NumPy as NP, and then we call the random function and then the random seed. So we seed it so that we always get the same output. But sometimes libraries can change. Maybe NumPy could say 42 could mean something different. And so when we update our system, because these libraries are always updated, when we update that library, we may have a situation where we'll have a different output. And so this might not be the best approach, but it's a very commonly used approach. Another approach here to create a test set is to use hashing. So it's like a form of encoding. Like, let's say you have a number 1, you represent it as XXY 23, and then Z XY, things like that. So it's a computerized approach to just represent things and like that. So in this portion here, what we're doing is we're creating our test set if they meet a certain hash range, something like that. So that's another approach to creating our test set here and things like that. So let me leave the create a test set. Please get the textbook, go over these things. You enjoy it. I think you enjoy it. And then you could really understand in deep detail some of these things. So I'm going to go to this discover and visualize. So after creating the test set, you visualize. Here we're just plotting the longitude and latitude like I showed you in earlier during the presentation. Here it's not really cool. We can't really understand a lot of things. It just feels like so many things are being plotted here. Now we apply what we call alpha, which is basically showing you the concentration in different positions. So values here are more concentrated. Longitude and latitude values are more concentrated here. Alpha shows you the level of concentration. But then we could even move much further, like I showed you in the previous image. And then we have more informative visualizations, like here, median house value, where I showed you houses closer to the coast, which you see over here, more as 0. So these are cool ways to just visualize your data and just understand it first. Then we look at correlations. In this point here, what we're doing is we're exploring how the median house value correlates with the rest of the features in the data set. Of course, it correlates itself very strongly. Median income is high in correlation with median house value. And so what this means is as median income is increasing, because it's positive here, as if you remember the going up, as median income is increasing, median house value is increasing. Or as median house value is increasing, only people that have a higher median income can get that house. And that makes a lot of sense. Excuse me. So when we visualize over here with the scatter matrix, as I showed you previously, you can see median house value is going upwards in this direction when you median income and median house value. Now this is we're just printing a specific plot. So you see median income as our X, and median house value as our Y. Again, we're saving all of the images. If you remember the save figure method I showed you previously. Now, over here, if we plot the correlation matrix between the total number of rooms and the rest of the features, what we observe is we can see some of the other features in this data set are highly correlated. For example, total number of rooms is correlated with total number of bedrooms. And so what judgment can we make here? Isn't this a redundant feature? Do we really need this total number of bedrooms? Or do we combine this total number of bedrooms? You can also see households here is highly correlated to the number of rooms. So the inference or the judgment that was passed from the textbook in this particular set of code is to combine these features. And so rather than having just total rooms by themselves, we could have total rooms per house, total bedrooms by total rooms, and population by household. So we're creating new features, and eventually we drop these other singular features. So we don't have things like total rooms existing. Rather, we have total rooms or rooms per house, which we call over here. So we drop this feature, and rather we keep things like this. So this is a way to data cleaning process. Now, now when we come to data cleaning itself, sorry, this was feature combination. When we come to data cleaning itself, when we have missing values, if you remember I mentioned earlier, total bedrooms had missing values. There are 3 options we could take according to the textbook. It could be more. One approach is to drop all the missing values. Drop all the rows with the missing values. Another approach is to drop that total bedrooms totally. Another approach is to fill in those values with their median, for example, and things like that. So in this set of code, we explore every option. Here we select the option 1, which we drop all the rows with missing values. And so when we drop all the rows with missing values, there are no rows with missing values. This is option 1. We're trying to see if any other row is actually existing that we should have dropped, and none is existing. Option 2, we drop the column. So let me see. 1 second. Yeah, so we drop the it's not shown clearly here. But the option 2 was to drop the column. And then we have option 3, which was to fill. So total bedrooms, rather than have null, we're now filling all the null places with the median value, like we see over here. Now, another way to impute values is using the simple imputer library in sklearn or scikit-learn. So this is just showing you some imputation approaches that are being applied. So with the simple imputer, we can calculate the median for all the sets of numeric features. So for latitude, it's this. I don't know if that, I believe that if latitude was the first feature, this is it. If longitude was the next, and things like that. So we're just splitting the statistics after it's calculated all the median values for each of the individual numeric features. So that's what we see. And then for the numeric features, we can transform it to impute these median values where there's something missing. So after we've done that imputation, we pass it to a variable called x. So what are these features in which we imputed? We have things like their numeric, longitude, latitude, median age, median income, and things like that. Excuse me. Now, after we've done the imputation, here is just creating a data frame using the numeric columns. So, and then it's plotting it here. It's plotting some of those rows from the numeric columns. I'm just moving quick so I don't waste a lot of time. Now let's come to categorical features. What the code is doing here is it's showing us how one way to handle categorical features. So if you remember from some of the first lines of code I showed you, there were no missing values in the categorical feature. Rather, it was only in total bedrooms. So here is just it's counting. So no, it's printing only the first 8. Remember head? It's printing the first 8 rows for that feature. So nearby, and I mean nearby, 1 hour from the ocean, things like that. Now, because I mentioned, if you remember correctly, machine learning models cannot use text. Rather, they use numbers. So here is using an ordinal encoder to actually encode, excuse me, these text values. So ordinal encoder, we're transforming the categorical aspect of the housing data. So it's printing the first 8 here as well. So if you look correctly, this was what it was before. This is the encoded, and it's showing you. So if you look here, 0, 1, 2, 3, 4. So 3 and 4 should have the same type of coding. So 1, 2, 3, 4. 3 and 4 here have 1 and 1, which is telling you that they are encoded in an ordered form and they have the same value. Now, on the other hand, we also have one-hot encoder, which is another approach. So we apply one-hot encoder to the categorical features in the data set. So it gives it 1, 0, and things like that. And as I mentioned earlier, it also creates new columns. So ocean proximity was the original column, but now we have ocean proximity inland, ocean proximity near bay, and 1 is true and 0 is false for where it's actually occurring in the data set. So for example, if I go over here, if I applied one-hot encoding, and so if I have a new column called ocean proximity here that is added, where we have things like inland, if it's ocean proximity inland here, at this row, we have a 1, 1, and we also have a 1 here. So that's essentially what's happening over here. Now let's go to feature scaling. I think I heard someone mention mice. Another approach as well to that's an imputation as approach, my bad. But we have in feature scaling, as I mentioned earlier, is basically a way to transform your data from a skewed form to a form more suitable for your machine learning model. A lot of things that happen in reality follow this distribution. And so these machine learning models are created in a way that they could really understand reality. So when you have data that's skewed in a certain direction, you want to transform it. When you have a numeric feature, you want to transform it to a form that is that looks similar to this. So we use things like min-max scaler to transform transform the data. We have things like okay, I'm conflicting two things. Okay, so we have min-max scaler, which is a way to remember the age and salary thing, put everything in the same scale. So this is a normalization approach, min-max scaler. And then we have the standard scaler, which is to put everything in similar scales. So normalization is from 0 to 1. All the numeric features values will be between 0 and 1. And then standardization is between -1 and 1. So we're just transforming the numeric features here to that. And then over here, we're applying log transformation, which is another feature scaling approach. So our data is no longer in this shape to something more of this shape. And so there are things like that and all that. So let me come to the custom transformers. Custom transformers is a way to customize your preprocessing approach. So you have, for example, a function transformer where you use you use a function. So let me piggyback a little bit. A function is essentially a block of code that is tasked with a particular action. A function is, for example, if I'm trying to cook food, I have a pot. A pot could be a function, because a pot is designated for cooking, right? The spoon could be a function on its own because the action with the spoon. So that's so we have functions that like log transform function, which you see over here is from NumPy. So that's a specialized block of thing that does a specific thing. So here we are creating a function transformer and we're passing the function and we're transforming the population feature in the housing data set. So that's what this function transformer is. Here we're doing like radial basis function, and I'm not going to go into that. You could learn those. And here's just doing similarity clustering and things like that. Then, transformation pipelines. In transformation pipeline, now what we're basically doing is we're creating a pipeline of what transformation we want to, see on certain features. So in this NUM pipeline, in the numeric features, we're doing imputation, we're doing standardization. So imputation, we're putting in values, and standardization, we're standardizing the values. So we're creating a pipeline that starts with imputation first, and using the simple imputer, and we're using the median, and then after that we standardize, right? So that's what this transformation pipeline is doing. So it's also from sklearn or scikit-learn as well. And then we could do some nice visualizations of the pipeline here to see the sequence of execution. So that's that. I'm gonna move and all that. So that's pipeline and things like that. So now, after you've done all this preprocessing, you've done so many things and things like that. If you look over here, you could see Previously, we had total bedrooms, but right now we have, after all the pre-processing, we have things like bedroom ratio, rooms per house ratio, people per house ratio. We did some radial basis clustering, and so it created new features that were clustered to certain points in the data set. So we created new features and things like that. We see the one hot encoding here, where we had ocean proximity inland, ocean proximity island, ocean proximity near bay, and things like that, ocean proximity. So this is what one hot encoding does. So this is an example of a pre-processing that's actually been done. And this is sort of the finalized set of features. So you keep doing this thing till you reach a point that is suitable enough for the context in which you want to apply the model to. In fact, a common thing that a lot of data scientists say is 70% of your machine learning work is on data preprocessing itself. So garbage in, garbage out. So once you do good preprocessing and then you apply this model, you have good results. In fact, in machine learning space, you hear people that talk about, oh, I have machine learning models. For example, they often mention things like neural networks or XGBoost. They say, I don't need to do a lot of preprocessing to give me good results. I beg to differ. If you give bad data set to your model, you have bad results. So preprocessing is a critical component of the machine learning pipeline. So after you've done that and all that, you now select a model. And that was the reason why I mentioned, is it supervised learning? Is it unsupervised learning? What are your evaluation metrics you want to evaluate with? So those are some things you have to gather and know before you actually apply the model. Those things will inform the model selection. So because in this data set, what we're really predicting here is the labels or the housing cost, right? Housing labels, which is the housing cost. That will be our target feature. And then the rest is our input feature. What you don't see here is this housing here. If you look here, that's our X, as I showed you previously, and this is our Y. This housing was assigned to an X value. If you go up and trace it, labels was assigned median housing value. So we're importing a linear regression model because we're predicting numeric values. So we do regression. If we're predicting classes, we do classification. So we import linear regression. And here we're creating a pipeline of preprocessing. So remember the pipeline we created? So every function that was in this preprocessing pipeline will run on the data, and then we also apply the model. So after it does all the preprocessing, it applies the model. So what's happening here is just creating an instance, essentially, a pipeline instance, and we assign it to the value of linear regression. Then when you call the method linear regression.fit, this is where we fit the model. So it fits all the transformers one after the other and sequentially transform the data. So we fit the model here, and this is where the training happens and things like that. When we talk about supervised learning much later, we're going to talk in much detail on what happens during the training process. So here, by calling this fit function, we're doing the training itself. After we've done the training, we'll now make predictions. So what's happening here, we're predicting the first 5 values, so 0 to 4. So if you look at your housing data set.
And Justin, we should be wrapping up.
Yes.
We just hit the 2-hour mark.
Okay. All right. I'm basically at the last portions. Thank you.
Thank you.
So housing, when you're predicting, we're predicting the first housing values, right? That's 0 to 4 here. And these are the values that are predicted. However, when we look at the actual values, these are the values, the first 5 values. So this is what our linear regression model told us the housing value is, but this is what the actual value is. Now, when we look at the error ratios, we can see for that first row, first input, we had a very high error value. And so that informs us that we need to do extra processes and things like that. So in this, for this linear regression, we use RMSE, which is root mean squared error. It's of L2 normalization. That's something else. But yes, so in this code, to wrap up, in this code, there's so many. So here they use linear regression and they use RMSE, root mean squared error. They also use decision tree regressor. And I think they use random forest as well. All right, so that concludes my teaching. I have some practice questions that I'd love you to answer, even as I end, and all that. So I don't know how the sequence of execution is, Tabiri, if you could tell me.
This just show it in the video, and those that watch it later will just answer it and send it in as attendance. So those that are here, they are good.
Okay, so these are the practice questions. I have 4 questions. What is the main goal of data processing machine learning? And you have multiple choice. Second question, why do we split a data set into training and testing? Third question, in a data set used for predicting house prices, which of the following is most likely the target variable? And then the last question is, why do we normalize or scale features before training a machine learning model? So with this, I conclude my teaching. I really hope you enjoyed it. I'm very passionate about machine learning, and so I'm excited to talk about it. Thank you.
Yeah, so thank you very much, Justin. And for everybody that stayed to the end, there are a lot of codes that you have to go through. And the most important thing is the basics of Python. And we are also going to do a project where each of our facilitators will work with you on a small project. And they will schedule their own times with you in between the Fridays we are not meeting. And they would help you go through all these processes. So they will have a data set. They will go through with you to process it, and then go to the end with you on to do predictions and all that. So go back to this video, watch it. The code will be made available for you. The notebook will be shared for you to be able to use. And the most important thing is, if you need to perform an action, you just go for the code. You don't need to write the code. You just write the line, get the line that does the thing for you, and then it will perform it for you. Next week, we are going to look at feature engineering. So if you have data, how do you make sure that you put it in a way that the machine learning algorithm will understand? And another facilitator will come and take us through. So thank you very much, Trustin. Thank you everyone that stayed behind. Please go back. The video will be posted. Go back to watch the video. Take your time with it. And let's have a successful learning. All right. God bless you, and see you all next 2 weeks. Bye-bye.
Thank you. Thank you so much.